So a bit more of mathematical induction. We'll go back to, well, what amounts to set theory. So let's finish this proof, which is simply about this n cubed plus 3n divisible by 3. Okay, so there is really no trick other than the idea of proving by induction, because if you think about it, it is kind of sometimes, in comparison to what we started with, remember I actually proved this thing first without the induction. Okay, so, well, when it's, in fact, not only that, you can actually visualize the proof right there. Okay, so, and in fact, that kind of gives you even the idea of how you can discover the proof. Okay, so that is not generally the case. It is just sometimes things more challenging than that, and so that is the proof, which is you can try certainly try to prove that it is divisible by 3 without the induction, which means that you will look at this number as it is, and then what do you do with it? We do know that well, I just don't see how it can happen, frankly. Certainly nothing on the surface. You might have to invoke some theorems from number theory in order to prove it from scratch. However, as you can see, what induction does for us, the method of mathematical induction does for us, it is only we can concentrate on the transition from the number to the next. Okay, so only that gap is we have to take care of. And that's exactly what happens. So the key part is, of course, the proving the inductive step from the inductive assumption. Okay, so the inductive assumption pretty much always exactly the same as what you try to prove, right? So that Pn over here. So the statement itself is Pn itself, and then that I get to Pn again to repeat it here. Okay. So once again, the only thing that I did is to translate the verbal description, divisibility by 3, into an algebraic description. So I put a 3k equal to multiply 3k 3 times k. So using the definition of divisibility. Okay, and then I clearly stated the what I would like to prove, Pn plus 1, replacing each n with n plus 1, right? So n cubed plus 2n replaced with n plus 1 cubed plus 3n plus 1. Okay, so and then once you see that, it's about the same question about divisibility by 3. So when that's the case, then so one number is divisible by 3, and you need to show that the other one is also divisible by 3. What do? You subtract them, and the difference should be also divisible by 3. So can you show that the difference is divisible by 3? And if you can, then you're done. So that's pretty much what we did here, except a slightly more subtle way. It just happened we follow that path. The easiest way is to expand my n cubed by the binomial formula. You know the binomial formula, right? So this one is for third power. Expand and then just simplify. You don't only have to simplify as much as you need to recognize that number that we already we know to be divisible by 3. You see it here, n cubed plus 2n. Okay, and then you substitute. So it is divisible by 3k. Okay, and then we end up with, as you can see, a bunch of 3's. You can if you want to be really sticky, you'll just write 3 times k plus n squared plus n plus 1. Okay, so that explicitly represents the number as a multiple of 3. Okay, so, and that is the end of the proof. Any questions?
Okay, can you go back to the 3k part? How did we get 3k again?
It's from the definition.
Okay.
By definition of divisibility, We just replace it with 3K. You could, there's certainly there's a variety there how you can handle it, but certainly when you do algebra, then it's better to replace words. It's inevitably the problem is about algebra. So if you do algebra, probably words better replaced with some kind of formula. So if you plan ahead, so replace divisibility with that 3K. Okay. Okay, so I'll do one more example. It is actually from calculus. So it's the power formula of derivatives. So it's calculus 1. Xn prime is equal to n xn minus 1. N is an integer. Well, let's say it's just like this. Okay, so positive integers. Okay, so do you remember how it's proven, or whatever the approach was taken in your class? Typically one way just to sort of discover the pattern, do it a few differentiation, and then have your teacher just suggest that there's a pattern there, and then you just come up with a formula. You have to prove it sooner or later anyway. So one way to do it is probably not the way you do it in class, but so let's do it a simpler way, just to as an illustration for the okay, I'm sorry.
Yeah. Why does n have to be positive?
No, but I want to concentrate on the proof that part of the formula that is actually especially applicable to proof by induction. So if you go with fractions, that's not so easy. If you go with fractional, especially real powers, then it's not so easy. Negative powers, yes, but then you have to go backwards. So you can do it as an exercise. So okay, so let's prove it for in the lemma is in fact the product rule. F times g prime is equal to f prime g plus fg prime for any two differentiable functions f and g. Okay, so proof, not of the lemma but of the theorem. The lemma is that we're going to use, and so you want to state it separately in order to, technically it would have to appear before the theorem itself. And then start with dimension 1, so base of induction, you have x1 prime is equal to, as you know, 1, and indeed 1 times x1 minus 1 is equal to 1, so it checks out. Yes, it checks out. So the base of induction is there. So the P1, okay? The assumption, inductive assumption, which is our formula that we're trying to prove, Pn, and then we state Pn plus 1 to be proven. The step of induction, xn plus 1 prime is equal to xn, so n plus 1, x n plus 1 minus 1. Okay, so this is to be proven, so you don't want to state that too strongly. You can actually don't even state it under these circumstances. You could just derive the formula and realize that by substitution, just the way we did last time, and then you realize that things work out. So what I'm suggesting to do that, so we can sort of hide this as the one what we are after, and then just substitute. Substitute whenever necessary. We apply naturally the product formula. So I'm sorry, product rule for product formula, same thing. So x times xn prime is what we're talking about, right? So that perfectly aligns with our idea of proof by induction. That is one extra step, one extra power, moving from xn to x plus 1, and that extra x is what we need to take care of. Okay, and so by the product rule, we have x prime times x prime times xn plus x times xn prime, at which point x prime is simply 1, but that on the right, on the second term, I am using the inductive assumption, right? So I use Pn over right here. So it will be x times nx n minus 1. Right? Does it look okay?
I thought that's what we're trying to prove.
But what's in blue brackets is what we're trying to prove. Pn plus 1. And we just, how do we get there? Just move the stuff around, right? So
Right now we're assuming the power formula is true.
well, yeah. For that's a kind of a way to put it. That is sounds like we're doing circular reasoning. We're proving power formula by by assuming that the power formula is true, but it's not. It's not, right? We're assuming it for n. For each n, one at a time, you can assume that it is true, and then you prove that the next level is also true. Okay? So we do not assume that Pn plus 1 is true. So if you want to think in terms of contradiction, you can say that, well, we know that up to some point the formula is true. Let's suppose the opposite, and then n plus 1, it's not satisfied anymore. Is it really true? And we discover that it's not. So we discover that a contradiction. We discover that, yes, in fact, it is. If this is not true, then let's try to go down and see at what point we have this situation when at the nth level the formula is true and plus first it's not. Is it possible? So if you want to see contradiction here, you can also be proven by contradiction. And there is some point to it, so that it would be clear that you're not doing circular proof. But because especially the way it was put suggests that maybe we are. Okay, but well, that's the logic. Logic is fine. So I have 1 times xn plus n times xn, which is 1 plus n xn. That's it. That is Pn plus 1. End of proof. Okay, any questions about it?
What do you do when you use PN? How do you
Right, so this is where it happened, right here.
Yeah, but how did you get from xn minus 1 to xn?
Well, because there's an extra x over there. X times xn minus 1, the power goes up by 1, right? Okay.
Oh, okay.
Okay, let's take a quick look. We know that the formula holds for negative n, so since it was brought up, the formula exactly holds for n equal negative 1, negative 1, negative 2, negative 3. So naturally it will be reversed. The induction will be reversed, so we will be going down in powers. which doesn't make any difference. So, and once again, you apply the power rule, right? So you need the base. The base will be slightly more complicated, but suppose that we know that the derivative of 1 over x prime is equal to negative 1 over x squared, which fits the power formula. Okay, and then what's going to happen is what is going to happen? Just try to look at this and tell me what you see. So I already have the base. The assumption is also, the formula is exactly the same, only n this time is negative. So what changes?
What did you say?
What about the proof changes when we start doing negative n's? What? Any thoughts? Well, let's confirm that the base is known. Okay, you can do it from the limit. Remember, 1 over x derivative is negative 1 over x squared. That's done pretty much from scratch. Okay, the assumption is just a technical pronouncement. That's the second line in the proof. Then we need to prove the next stage, the step of induction. Okay, so the formula is exactly the same. No, wait a minute. The formula is the formula is what happens to the formula is that the power is going down, not up. Okay. So the step of induction then will not look like n plus 1, but rather n minus 1, right? Over here we'll have n minus 1. So we're going from 1 to negative 2, negative 1, negative 2, negative 3, then negative n, negative n plus 1, negative n minus 1 rather. Okay, so I have to fix it here. So let's say n is still positive, but we are looking at what we're looking at is the formula that is, well, I guess I'm just jumping to conclude like this. This is the formula we're talking about. Okay, it's the same formula, only I'm using negative n's. So because of the proof by induction, we have to n has to go up even though the power is going down. Okay, so you see how this formula is exactly the same as our formula, the original formula, as it's supposed to be, but it's not covered by our proof because n was assumed to be 1, 2, 3. Okay, so now it's assumed to be equal to n, still 1, 2, 3, but the formula is different. So because we are differentiating negative n. So then when we proceed from n further, whether it's negative over here, becomes negative, we proceed by subtracting 1. And subtracting 1, what does it mean? It means division. Okay, so what does it tell you? How do we handle division? What do we have for division in calculus 1?
Quotient rule.
The quotient rule. So instead of the product rule here, we will use the quotient rule. Okay, but other than that, so over here I'll have x negative n, 1 over n. And so divided, 1 over x. Okay, so that's division by x, and we could, as you can see, altogether x negative n divided by x it is actually the power of x negative n over here. Okay, so the point was to break it into two in order to apply the theorem of the quotient rule to begin with, and then they still apply the assumption of the induction. Okay, so I don't want to go too deep here, and let's just I want to make it an exercise. So exercise. Product, or rather power formula for n equal for negative powers, just like this, for negative integer powers. It does not work, the induction won't work with with any kind of fractional powers. So even though I know that the derivative of x is 1, or the rest of them are supposed to be known, what do I do if I have square root of x? It doesn't help really. So another exercise is actually you can prove, and that's usually the way it is done in calculus. It is from scratch. So power formula, the same power formula. So once again, for same as original, but different proof, where it relies on the once again the binomial formula. So you start from scratch. To find the derivative of a function like that. It will be limit xn minus an over x minus a, like this. Okay, with x going to a. So that's the definition of the derivative, and your function will xn, and then you need your binomial formula for the numerator in order to simplify this, to get rid of the denominator, and then take the limit. Okay, so the binomial formula comes in here in order to simplify, and then eliminating the denominator, and then set x equal a, and then you're done. All of a sudden you have your formula. So you might remember how it was actually proven in class of something, in calculus 1. Okay, so once again, the binomial formula for nth power is a long expression. Okay, the binomial formula that gives you, when you divide that numerator by the denominator, you end up with the n plus 1 terms. And then what do? You just plug in a equals x, and you have your the formula that we already know. Okay, so where is the induction? The binomial formula is proven by induction. Okay, so if you want an exercise, prove the binomial formula by induction. So, well, just if you don't remember, remember that's how it starts. X, I should put it, a plus b nth power starts with a to the n plus an minus 1b. Remember this one, right? The binomial formula on the left term is b to the n. Okay, so that formula is proven by induction. Okay, and then you can apply it to prove the power formula from scratch, from the definition of the limit, which is always better than this. But the purpose of this example of the theorem was just to illustrate the what induction does for us. Here's another exercise for you on the subject. Okay, so the angles, the sum of the angles of the triangle add up to 180 degrees. Okay, but what about the square? The triangle is the unknown. Pi, and square or rectangle is what's the sum of the angles of a rectangle? 2 pi, and that actually applies to all rectangles. I'm sorry, not rectangles, quadrilaterals. Okay, so it doesn't matter, the shape doesn't matter. And then you go with pentagon and so on. So there's pentagons, hexagon, it doesn't matter. There is a formula, and so the sum of the angles is of a polygon with n sides, or n gon if you like, is n minus 1 pi, n minus 2 pi. Okay, same story, proved by induction. So the base is there. That's the triangle is the base, so you can assume that. So any thoughts? How you would approach it? When you don't have a big idea, don't try to jump to nth dimension right away and look at the lower dimension. For example, if you know that the sum of the angles of the triangle is pi, how do I proceed to a quadrilateral? It is an inductive step in the situation that is still most manageable. So how do you do this? This is the inductive step at its simplest. How do you prove that the sum of the angles of any quadrilateral is 2 pi? You cut, right? You take the quadrilateral and cut it in half with a diagonal, right? So if I have a quadrilateral of any shape, I cut it like this, right? And I have pi here and pi there. Well, that's the end of it. But so the challenge is just to write out in such a way that it is readable, appropriately written up as an actual proof. Okay, so that's another exercise. Okay, so we're back to set theory, specifically to the part that is unavoidable, and it takes it to us to the next level, and that is functions. So that I mentioned that last time, and that is or last week rather, and it is about functions of one-to-one onto to begin with. But let's start from scratch. So functions are, in the context of set theory, functions are simply functions of sets. Okay, so there is no structure. Functions on sets. Just as sets don't have any structure, these are no numbers, not vectors, no nothing like that. So we have to be able to handle them in the most abstract. And then the next level is to look at the functions between sets. And once again, we have to handle them appropriately without referring to anything that is we are used to in calculus. So it's usually numbers. So okay, so this is the notation. Okay, so x and y are sets, and f are names of sets, and f is a function. Okay, so as you can see, there are no restrictions whatsoever on anything. Okay, so x is the domain of f. Okay, so what does it mean? It means that whatever element of set x you pick, and the f of x makes sense. So f of x is defined for each x in x. And then since what's the point of y here, and then defined in what sense, f of x is an element of y. So that is like the definition of a function. No reason whatsoever for us to make it any more specific than that. So so as you can see, there's a departure from calculus approach. That with the discussion of the domain, especially, we are not going to be having this concern about whether this particular number is in the domain of a function. So what is the domain of x plus sine x or something like that. So we don't care about that. So if we already have a set, we have to have a set before we have a function. Okay, so we do not go from some kind of formula and then try to find the domain. The function is in fact a triple. So it's we say f as a function, but really you cannot speak of a function unless these two are also defined, the other two. So a triple. Domain, the y is sometimes called the codomain. Or if of f, or if you prefer, then these two might be called also the set of inputs and for x, and the set of outputs of possible outputs. You know, so the codomain is not the same as the range. So you can miss it. You can miss some of the elements. So if this is x and y, you don't have to hit every one of them on the other side. But you do have to have every element of x to be taken care of by f. Okay, so that's the illustration that you might remember from pre-calculus. You've seen this kind of ovals with arrows from before calculus. There is no point of doing that in calculus itself, because especially in calculus 1, every x and y are real numbers. That's a typical situation. Is in calc 1, x is a subset of r. So you have a formula, then you work it out and find out for each values of x that makes sense. And you don't have division by zero, square root of negative number, something like that. Then you find what the domain is, and it is usually a subset of R in calculus 1. And definitely y is definitely R. There is no concern anymore about whether or not we are hitting the whole the whole R. So we can just as well take the whole R. Okay, so some of you are still taking calculus 3, right?
Yeah.
Okay, so that is where you already start feeling seeing the difference. Calculus 3 is functions become more complicated, and both inputs and outputs are not real numbers anymore. Okay, so that picture, this little picture that is becomes so ubiquitous when you think about functions is not. You already see that it's not general enough in order to handle situations that are required entirely by calculus. So, for example, if you're talking about parameter curves, then they already could on the xy plane. You could have something like this. So a function of, say, a parameter curve. So a parameter curve would be the x is still a subset of R, but y might be, say, R squared. Okay? So then you can see how easy it is, if you think about it, how easy it is to miss points on the plane. So if your starting point is real numbers, there, in a sense, there are fewer of them if the function continues to go around. So it is hard to imagine, even though it's possible, to imagine a function, a curve that actually covers every single point on the plane. You may have seen those. Have you seen a space filling curve? Okay, another mind expanding idea, but let's do it one step at a time. So typically the parameter curves that you see, and they're differentiable. That I guess that's what the important about it. They are far apart, so you could this is This is what I'm talking about for a curve to fill the whole space is hard to imagine. Well, even if it might be possible, in some sense, we are not concerned about that because, well, this is just an example. So an example is then we're missing a lot of the codomain, the outputs, and so then what is the meaning of this? Even though we keep calling this the range, another better word is the image. The image of f. So that's what it's called in mathematics. All possible y's. Okay, so that's the definition. The image of f, x to y, is the set of all possible outputs. So in other words, this is how sometimes you simply write I am f, and so it is y's, such as that, y is equal to f of x for some x in x. Okay, so in other words, it's an existence thing. So a y belongs to the image when there is an x, input x, that gives you that value. Okay, so it's a very, very familiar idea from Calculus 1 when you talk about the range, except usually range was something simpler in whole lower dimensions. Now it could be some small part of the target space. Okay, so that is the image. And then related to the idea of the image is the idea of a function that is onto. Remember this one, x for x to y is called onto, also surjective. If, remember this? What is the image of a surjective function? Onto. It covers everything. So the image is everything. You do not miss anything. So the image of the function is the whole space of outputs. So that's what makes it onto. So that certainly is a good idea to think that way. Well, let's think of examples first from Calculus 1. Onto, how about y equals 2x? This one is onto. A function from R to R is onto. So the domain is everything. Y equals negative 2x also is good. But y equals 0, not 1 to 1, because what's the image of function y equals 0? No, you're speaking of the graph. The image is 0. So the image is of f is a single point. Well, since they just came up, let's add an extra definition here, the graph. So f from x to y is given. What is the meaning of the graph in the set theoretic setting? Well, before we even define it, let's think about it for a moment. So the graph as opposed to the image. Once you start thinking that way, it helps. So what is its graph as opposed to the image? So what is why the image is not really, it does not capture everything about the function. I mean, think about functions in dimension 1, the meaning of the range, what does it tell you? Those function y equal 2x, the image is r, y equal negative 2x is also the image is r. So the image does not tell you what the function is. The graph does. Right? So y equal 2x this way, y equal negative 2x that way. So the graph contains all the information about the function. So you can calculus 3, you might remember once again parametric curves, which is kind of more complex, but think about function of two variables. What's the graph of a function of two variables? typically? Two variables, which means what's the domain might be the plane. Function of two variables, the domain might be the plane. In the meantime, the range, or the codomain, is still the rails. So what do you think is the what is the graph? Anybody from calculus 1 you should remember? Well, the graph collects x and y's together in one point. Okay, so that's why you have f from f of x is equal to x squared, y equal to x squared. So the graph is all x's y's pairs xy. The graph is located in the xy plane. The function of two variables, and then both input and output x and y are both present simultaneously in the graph. Okay, so the graph is xy's with y equal x squared. That's really uncomplicated if you think about it. So that's my what the graph is of a function of one variable from calculus 1. That's how you define it. Those xy's on the xy plane. So this is lies in our plane. XY plane, and so all pairs XY for which Y is equal to X squared, that's what the graph is, all of these pairs. Okay, so in the meantime, so then what is the graph of a function in general? And the answer is it's exactly the same. You just have to combine things together into pairs. So generally, the graph is of the graph of y equal f of x is the set of all pairs xy with y equal to f of x. Okay, so if you have a function of two variables, then the inputs. So here you collect all inputs and all outputs in one. Inputs, outputs. Okay, except in the function of two variables, you have your inputs lie in the plane. Okay, and the outputs are the z-axis. Okay, so taken together, that's why your graph of function of variables lies in the three-dimensional space and is the surface. So, so say f from R2 to R, this is its graph. Inputs, a whole plane, and outputs only a line, only the z-axis. Okay, but then you connect. You pick each point here, and you provide what? You provide the altitude. So if this is xy, well, let's call it x capital, and then you elevate it above the xy plane to the height of f of x. Okay, so that's if you do it for every point in the domain, you will end up with a surface. Right? So does it sound familiar? Okay, so that's how it happens, and it really graphs capture so much information about the function, all information about the function, and you also can look by looking at them, you can actually tell them apart. The different typically the types of functions are different. So over there, the graph of a function of let's say y equal x squared, it's a curve. Function of two variables is a surface. Altogether might look like this. Okay, like this, a surface. Parametric curve is a parametric curve, and so on. Unfortunately, at some point we run out of dimensions. We cannot visualize them anymore, but the concept of the graph remains. And what we do with it, just to mitigate the fact that if I go with say a function of three variables, I already where does the graph of a function of three variables lie? You have x, y, and z are the independent variables, and then there's the fourth, which is the dependent variable. So altogether, the graph lies in the four-dimensional space. Okay, so we cannot visualize it anymore. Function of three variables, a vector field. Also, you need most of the time 4 dimensions in order to see its graph. So what do we do? Well, to mitigate that a little bit, we look at the image, which requires lower dimension. So for example, if we're talking about parameter curves, we could throw out, look at this is the image. If I throw out the independent variables, then say a function might be equal to, say, sine t cosine t. Does this one look familiar? Sine t cosine t, a parameter curve. Okay. What is its, so as you can see, the t is the input, so it is a function from the reals, but it gives me two outputs, a pair of outputs, x, y, so this is the output. The function is from R to R2. That's what the plane parameter curves are. And then if you look at the image, it is a curve on the plane, which is, what kind of curve is this? Sine t cosine t. It's a circle. It's a circle. So, but what happens to with that circle? You trace it how many times? Infinitely many times. If you pick every value of t, you will keep going. You go on and on. When you reach to pi, you are back where you started, and then you keep going. Which means that you retrace it infinitely many times. Which means that what does it mean? That well, so yeah, like I said, every point is covered infinitely many times. But this is not the graph. That circle is the image. So the set of all possible outputs of this function is a circle. What is the graph? It is indeed a spiral. That's right. So this is this is what you see. This is my t. This is my x and y. Okay, so t progresses. That's my input. The t is my only input. And these are my outputs. Outputs are the xy plane. So inside the outputs, where my circle lies, my image lies. And so if I stick to the image, then this is what I see. It is purely a circle like this. So in the xy plane like this. Okay. But what it is a shadow of the graph, which also includes every t. So it is indeed a spiral which goes off in the manner that maybe like this. Okay, so once again, this is the graph of f, and in the meantime, this is the image. So clearly it's not onto. What?
Does this relate to that picture with the mirror that you were showing, like with?
Well, no, there was no the mirror. You mean there was no mirrors there? There were no mirrors there.
That picture was that you were showing.
Right, but there were no mirrors. There was identifications.
Not a mirror. With that picture. That's what I'm trying to.
I don't think necessarily. I mean, there is a circle there, surely. So you can make a connection if you like. Yeah. So.
Okay.
Is the image the same as the projection?
Projection of the graph, yes.
So
Projection of the graph on the set of outputs. The set of outputs is the purple one, and we take my spiral and project it, or have a shadow. Imagine that the light is coming from the right, then that circle that we see on the right is the shadow of our spiral. Okay. All right, so we'll see how far it goes.